We are diving into Black Box on Policy Distillation of Large Language Models, a paper that introduces a new method called Generative Adversarial Distillation, or GAD. And the core challenge here is a really fundamental one for anyone in the space. How do you create a smaller, high-performing student model from a huge proprietary teacher like, say, GPC-5 chat when all you have access to is its text output? You don't get the internal logics, no parameters. That's the black box problem.
And GAD comes in with a really elegant solution. It frames the whole thing as a generative adversarial network. So the student model becomes the generator. And then they train this other model, a discriminator, to tell the difference between the student's writing and the teacher's writing. This whole setup, this game they play, creates an on-policy reward signal. And that's the key. It means the student learns from its own generated responses without needing that fine-grained probability feedback from the teacher.
And the headline result, the thing that makes you sit up and take notice, is that GAD just consistently crushes the traditional method, sequence-level knowledge distillation, or CKD. Get this. A Qwen 2.514b student trained with GAD gets performance judged by GPT-4o that's right on par with its proprietary teacher, GPT-5 chat. It's a whole new way to think about black box distillation.
That's a huge deal. I mean, getting a 14 billion parameter model to perform at the level of a massive closed source teacher that's the goal, really.
Okay, let's set the stage a bit more, because to really get why GAD is so cool, you have to appreciate how hard the black box problem is. So let's start with knowledge distillation, KD itself. The basic idea is just shrinking a huge, expensive teacher model into a smaller, more efficient student, right?
Right. And in a perfect world, you're in the white box setting. You're maybe distilling from one open source model to another. The student has full access to the teacher's internals, its probability distributions, hidden states, everything. So you can use standard stuff like Kullback-Leibler divergence to just match the next token probabilities really precisely.
But that's not the reality for most people. The cutting-edge models are behind an API. That's the black box reality. Your teacher is GPT-5, you get text back, that's it. And suddenly, all those powerful methods that need to know the teacher's probability distribution, they're just off the table.
So what do people do? They usually fall back on sequence-level KD or CKD. And really, that's just a fancy term for supervised fine-tuning. You're just training the student to imitate the teacher's final text.
Which sounds simple enough, but it has some major problems. It's missing that crucial probability signal, and it can get tripped up if the tokenizers don't match or just struggles to learn the style instead of just the words.
Exactly. And that's why the field has been moving so heavily towards on-policy learning.
Right. The idea that the student needs to learn from the responses it generates, not just what the teacher generates. Why is that so important?
It's all about generalization. On-policy learning encourages what's called mode-seeking behavior. The model learns to focus its probability on a few high-quality outputs instead of spreading it thinly over everything possible. It also helps with exposure bias. If a model only ever sees perfect teacher responses, it doesn't know what to do when it makes a small mistake during generation. It can't get back on track. On-policy helps it learn to recover.
Okay, but that brings us full circle right back to the barrier. If on-policy learning is the way to go, how on earth do you evaluate a student's own unique response if you don't have the teacher's probabilities to compare it to?
That's it. That is the fundamental problem GAD is designed to solve. You need a reward signal, but you only have text.
Okay, so let's unpack GD. How does it conjure this reward model from basically nothing? It's a Jan-like setup. Student LLM is the generator, G. The magic is in the new part, the discriminator, D.
Right, and the discriminator isn't a giant LLM. It's a smaller, specialized model. Its only job is to look at a prompt and a response and output a single number, a score, that says how likely it is that the response came from the teacher.
So the student, the generator, is in this constant battle to produce responses that get a high score. It's trying to fool the discriminator.
And if you look at this from an RL perspective, a reinforcement learning perspective, the discriminator is the on-policy reward model. It's providing that feedback the student needs to learn from its own outputs.
That makes sense. But JANs for text have historically been a bit unstable. What's different here? What's special about the discriminator's objective?
That's where the Bradley-Terry loss comes in. It's a really smart choice.
Yeah.
So the generator uses policy gradient with the discriminator score as its reward. But the discriminator isn't just learning real or fake.
Okay, tell me more about the Bradley-Terry loss. Why is that better than just standard classification?
Because it's a ranking loss. It learns pairwise preferences. It's trained to make sure that for the same prompt, the score it gives the teacher's response is always higher than the score it gives the student's response. So it's not just learning a binary category, it's learning a continuous sense of relative quality. And that provides a much smoother, richer gradient for the student to learn from.
I see. So it's learning standards, not just labels. This sounds way more stable than, say, typical RLHF where you have a fixed reward model.
Oh, absolutely. That's the key advantage. In standard RLHF, your reward model is static. If the student finds one little loophole to exploit to get a high score, it'll just do that over and over. That's reward hacking. With GAD, the discriminator co-evolves. As the student gets better, the discriminator gets tougher. It's like the security system is constantly updating itself to counter the thief. It provides this dynamic supervision that keeps the whole process stable.
And speaking of stability, let's talk about the training protocol. They found that you can't just jump into this adversarial game from a cold start. They have a crucial two-stage process, starting with a warm-up stage.
Yeah, that warm-up is essential. If you just throw a randomly initialized student against the teacher, the discriminator's job is way too easy. It can immediately tell them apart, and the gradient signal for the student just vanishes. The training stalls.
So the warm-up is like a bridge to get the student in the right ballpark. How does it work?
For one epoch, they do two things. The generator gets a quick round of supervised fine-tuning on the teacher's responses, basically a bit of CKD. And at the same time, the discriminator starts training on that same data using the Bradley-Terry loss. This just ensures both models are skilled enough to start the adversarial dance productively.
And for the engineers listening, once they get to the main training stage, the reward is constantly changing. The paper mentions they use the GRPO algorithm for policy optimization. Why that choice?
Stability again. The reward function from the discriminator is non-stationary. It's always changing. An algorithm like GRPO is designed to constrain the policy updates so the student doesn't take a huge catastrophic step based on a slightly shifted reward. It helps to track the discriminator's feedback smoothly and efficiently.
Let's get to the experiments. The teacher was GPT-5 chat. Who are the students?
They used a range of open source models. The Quinn 2.5 Series 3, 7, and 14 billion parameters, and also Llama 3 at 3 and 8 billion.
And the data.
About 200,000 samples from a cleaned version of the LMSYS Chat1M dataset. And for evaluation, they didn't just look at simple metrics. They relied heavily on GPT-4o as a judge and tested generalization on totally unseen datasets like DALI and Vicuna.
Okay, so the results, the gap between GAD and the old CKD method is pretty huge.
It's massive. And what's really practical is the efficiency gain. The Qwen 2.53b model trained with GAD performed as well as a Qwen 2.57b model trained with CKD.
So you're getting the performance of a model twice the size.
Exactly, for the same compute cost.
But the real headline grabber is the biggest student. The Qwen 2.514b model trained with GAD scored a 52.1 from the GPT-4o judge. The teacher, GPT-5 chat, scored 51.7.
It's not just matching, it's slightly exceeding. It's capturing the teacher's competence with incredible fidelity.
And this all comes down to better generalization, right?
For sure. When you look at those out-of-distribution data sets, CKD barely moves the needle. Sometimes performance even gets worse. But GAD shows strong, consistent gains across all of them.
So why? What is GAD learning that CKD isn't? They did a really interesting analysis on overfitting.
They did. They looked at endogram overlap. How much does a student copy the teacher's exact phrasing? And what they found was CKD had a higher overlap. It was a better mimic of the surface level text.
But it had a lower quality score.
Right, which means CKD is just overfitting to the local lexical patterns. It's memorizing phrases.
Whereas GAD had lower n-gram overlap at a higher score. So it's not just copying words. It's learning the underlying style and how to follow instructions properly. It's replicating the competence.
It's the difference between memorizing a textbook and actually understanding the concepts. And this goes back to that idea of mode seeking versus mode covering.
A classic Jan concept.
Yeah.
How does that play out here?
CKD, because it's just supervised fine-tuning, is a mode-covering algorithm. It tries to spread its probability out to cover every possible answer the teacher might give and makes it kind of timid. GD, because it's RL-based, is mode-seeking. It learns to focus its probability on the handful of really high-quality responses that will fool the discriminator. It actively avoids the bad stuff. And for LLM distillation, that seems to be a much more effective strategy.
And the final piece of evidence, the stability analysis. They tried to break it by using a fixed discriminator, like a normal RLHF reward model. What happened?
It failed, catastrophically. The student almost immediately found a loophole. It learned that if it just generated super long, rambling responses like 1,300 tokens long, it could max out the score from the static reward model.
Classic reward hacking.
Textbook case. The fixed critic couldn't adapt, so the student just optimized for the flaw and its quality completely tanked.
And in contrast, GAD with its co-evolving discriminator.
Perfectly stable over thousands of training steps. It's really the definitive proof that the dynamic adversarial critic is the right architecture for this problem.
So what's the big takeaway for people trying to build on top of these closed source models?
It means we finally have a robust way to do on-policy distillation in this really challenging black box setting. GAD gives you that stable, dynamic reward signal without ever needing access to the teacher's logits. And what's also super practical is that it works even if the tokenizers are totally different. You could distill a model with some weird proprietary tokenizer into a standard Llama student, no problem.
It feels like the success of GAD suggests that the knowledge we're trying to distill isn't actually the next token probabilities. That's hidden from us anyway. The real knowledge is in the style and quality of the final output. And this adversarial approach proves that building a dynamic, evolving critic is a more powerful way to mimic that behavior than just static imitation.
Which leads to a really interesting question for the future. Given how well GAD works by capturing these global characteristics with RL, should future distillation research focus more on defining sophisticated adaptive reward models? Maybe we should stop trying so hard to guess the teacher's internal probabilities. The real secret might be in learning how to judge quality, not just predict tokens.